In this section, we're going to be talking about exponential functions and what they look like, what they graph. And then later on in this chapter, we're going to be looking at logarithmic functions and how they are inverses of each other. So let's get started. Exponential functions have the form f of x equals a to the x, where a is going to be greater than 0 and a cannot equal 1. So an example would be something like f of x equals 2 to the x, or f of x equals 1/2 to the x. Both of these are called exponential functions, and what really makes them exponential is the fact that the variable is the exponent. Now, one of the things that we're going to realize here is that these two graphs are very different, okay? So the first one, we're going to do f of x equals 2 to the x. And we're going to pick some arbitrary values of x, and then we're going to find out what f of x is. So we're going to do like -2, -1, 0, 1, and 2, okay? Now, off on the right-hand side, I'm just going to do a little bit of math. So we're going to let x equal -2. So f of x is going to equal 2 to the -2, which equals 1/4. Now, do the same thing, except now we're going to let x equal -1. So we get f of x equals 2 to the -1, or 1/2. All right, next, we're going to go ahead and do 0. 2 to the 0 is 1. And then finally, the last two values, when x equals 1, f of x equals 2. And when x equals 2, f of x equals 4. Okay? So what you can see here is, if I were to graph these points right here, -1, -2, 1 and 2, 1, 2, 3, and 4. There we go. So I'm going to get 0, or I'm going to get -2, 1/4. So that's going to be like all the way down there. -1, 1/2. It'll be like right about here. 0, 1, 1, 2, and then 2, 4. And you get a graph that looks something similar to this. Now, obviously, if you want to really make your graphs look good, okay, you can go ahead and use Desmos. And what you'll notice here is, I'll put it in projector mode. There we go. What you'll notice is, here's that y-intercept of 0, negative, or 0, +1. And if the values of x are less than 0, then you're going to creep along this x-axis. And if values of x are bigger than 0, then you really get big really, really quickly. We call this exponential growth, okay? So let me go ahead and let's put that in our notes. So this type of growth is called exponential growth. And you see this in like bacteria cultures. It'll experience exponential growth. You also see it in like investing, continuously compounding growth. Okay, where this just gets big really, really fast. Now, on the flip side, f of x equals 1/2 to the x. All right, let's see what happens here. Now, I'm not going to choose as many values here, because I don't need that many just to get the point across. But we're going to let x equal -2. So f of x is going to equal 1/2 to the -2, which is really 2 to the second, which is 4. Then we're going to let x equal 0. So we're going to get 1/2 to the 0. And 1/2 to the 0 is 1. And then finally, we let x equal 2 to give me x equals 1/4. And if you were to go ahead and plot these points, -2, 4, that would be like all the way up here. 0, 1, And then 2 comma 1/4 would be like all the way down there. All right. And what you notice here is it's the exact opposite shape. It like reflects itself about the y-axis. So we call this exponential decay. And like I said, if you really want to get technical with it, if you want a nice picture, go ahead and just use Desmos. And we'll go ahead and do 1/2 to the x. And notice in blue, we have the exponential decay. And the key is both of these graphs, or both these functions, regardless of what they look like right now, without shifting or translating or anything like that, they both have a y-intercept of 0, 1, which is really, really important. Also, and this is for both, if I zoom in on this x-axis, notice that there's always a gap, even no matter how far to the right you get. So I'm going to go ahead and exaggerate this. So we're going to go all the way. We're going to let our x values get really large, like x to the 50th. If I keep zooming in, and I'm zooming in and zooming in and zooming in. Oh, it won't even let me zoom in anymore. What you'll notice is these these functions will never ever cross the x-axis. Sorry, I'm zooming out a lot. There we go. Yeah, they'll never cross the x-axis. So that x-axis is what we call a horizontal asymptote. All right. So let me go back into our notes and write that down. All right, and here we go right here. So we got this nice definition that the book has provided for us. So the exponential function f of x equals a to the x, where a is greater than 0 and a is not equal to 1. It will have a domain of all real numbers. That means no matter how far to the right or how far to the left, you can always use an x value. That's really good. The range, and this is the important one, is 0 to infinity. Notice that the 0 has a parenthesis, which means we cannot include 0 in our range. And that is because the next sentence, the line y equals 0, is a horizontal asymptote of f. The graph of f has one of the following shapes. Now, if a is greater than 1, okay, so f of x equals 2 to the x, f of x equals 3 to the x, f of x equals 15 to the x, whatever, it's going to have exponential growth. Okay? Now, if a is between 0 and 1, in other words, it's a fraction, okay? Then you're going to have exponential decay. Now, with exponential growth, like I said, that would be like bacteria growing in a culture, continuously compounding growth, etc. Exponential decay is like half-life, or it's like the temperature of something cooling down in your room when you take it out of the oven. All these experience exponential decay, all right? And some examples would be like f of x equals 1/2 to the x, f of x equals even something like 3 to the negative x, all right? Now, with 3 to the negative x, you got to remember that you can rewrite that as 1/3 to the positive x using rules for exponents. So you got to remember that. All those rules for exponents still are there. They don't go away. All right? And just like in previous sections, we will have the parent function. We're going to call the parent function here f of x equals 2 to the x. Graph f of x equals 2 to the x minus 3 without a calculator. Okay? Well, remember, you got your parent function, which is 2 to the x. Now, I'm going to draw this in a dashed line just so we know the difference. So here's our parent function right here. And I'm going to get a little bit more technical now. We also have this y equals 0 asymptote. So you know, like, that's what it looks like, okay? Now, if I wanted to graph f of x equals 2 to the x minus 3 without a calculator, what I have to do then is I have to take this this y-intercept and this horizontal asymptote, and I need to shift them down 3 complete units. All right? So what this is going to look like then, all right, well, this will look like is the original y-intercept has to be shifted down 3 units. So it's going to go down 1, 2, 3. So my new y-intercept is going to be right here. And I'm going to go ahead and label it. You can see the big dot I'm drawing here. This is going to be 0, -2. Okay, that's my new y-intercept. And my new horizontal asymptote is now y equals -3. Okay, and that's what that graph looks like. So the vertical shifts still apply. The horizontal shifts still apply. Even if you reflect it about the x-axis, let's look at one that where it's reflected about the x-axis. That still applies. So if f of x equals 3 to the x, graph g of x, which equals -3 to the x. Now notice the negative sign is in front of the parent function. Okay, so this is going to be a flip about the x-axis. So if this is my normal, y equals 3 to the x, f of x equals 3 to the x. Then when I go ahead and I reflect it about the x-axis, everything changes. Now it goes down this way. This is going to be f of x equals -3 to the x. To be honest with you, the best thing to probably do is just go ahead and just use your calculator or Desmos. I know I said don't use a calculator, but go ahead and use it. It just helps. So the last thing that we're going to be talking about in this section here, introductory section, is going to be compounding interest. And there is a nice formula that we use for that. So I'm going to go ahead and copy and paste that right now. All right, here we go. And how compounding interest works is initially when you go into like a bank or something like that, and you invest money, the amount of money in your bank account after a certain amount of time is going to be the amount equals P plus PI. Now, A stands for the amount. P stands for the principal. It's how much you invested. And I stands for the simple interest. Okay? Now, once you invest a little bit of money and then that money is reinvested, okay, you're going to get something that looks like this. A equals P times 1 plus I, which is going to be your new investment amount, okay? So if you just keep investing over and over again, so let me write it down here. So A equals P times 1 plus I times your new investment, and you keep reinvesting the money and you keep doing this, you're going to get all the way to this general formula, which is P times 1 plus I to the K power. So notice that this is an exponential function with the base 1 plus I. The K is our variable. Okay, it's the thing that's happening. Like this would be 1, 1, 1, and you would just keep adding them up. So if I just stopped right here, that would be A equals P times 1 plus I to the third. However, we're going to let this money keep growing and growing and growing. And if we allow this to happen without bound, then we're going to get this P times 1 plus I to the K. Now, if the annual interest rate is R, so if interest rate is R, and if the interest is compounded n times per year, so it could be quarterly or daily, continuously, whatever, then I is going to be equal to R over N. And T is going to equal N times T in years. So basically, what ends up happening is you get this formula over here on the left. And I'm going to zoom in here so we can all see it. So this is compounding interest. A of T equals P times 1 plus R over N to the N over T power. Or I'm sorry, to the NT power. Where A of T is the amount after T years, P is the principal, R is the interest rate, N is the number of times interest is compounded per year, T number of years. Now, I will highlight this one thing because this is really going to play a major role here. Right here. Notice that I highlighted the quantity 1 plus R over N, and I also highlighted that letter N in the exponent because that is going to play a major role later on. All right. And you've all seen that before. It's just maybe you never knew that that's what it was as a definition. But anyways, here's our compounding interest formula. All right. So a simple, easy example will be something along the lines of a sum of $1,500 is invested at an interest rate of 12% per year. That's pretty good. All right. We're going to find the amounts in the account after 3 years if the interest is compounded. And we're not gonna do all of them, but we'll do a couple of them. If the interest is compounded annually, this way I can define what annually means, semi-annually, quarterly, weekly, and daily. So this is nothing more than just setting up a formula and then plugging it into your calculator. That's it. Now, annually means n is equal to 1. It's compounded once, and it's always compounded on the same day every single year. So for us, A of T is going to equal 1,500 times 1 plus 0.12 over 1, all raised to the 1 times 3 power. Okay? So we just get out our calculator, and we'd get $2,107.39. Now, semi-annually means n equals 2. So, same formula. It's just now, wherever we see that letter n, which is the number of ways it's compounded, we're going to replace it with a 2. Okay? So just give me a second here. I'm going to type it into my calculator real fast. Put a 2 there. All right, and we get $2,127.79. So not like we're making that much money, but if we allow it to compound twice, we make an extra $20. Quarterly means 4. So I'm just going to go ahead and just type this into the calculator real quick. So we get A of t equals 1500 times 1 plus 0.12 over 4, all raised to the 4 times 3, and that's going to be $2,138 and 64 cents. Weekly, n equals 52. Now, there is a weird one with weekly. I'm sorry, no, with daily. Daily's the weird one, and I'll go over that in a second. So weekly is going to be 0.12 over 52 times 52. Or, I'm sorry, raised to the 52 times 3 power. So I need to type this into my calculator again. So 52 there. And 52 down there. $2,149.10. And then finally, daily is 365. However, the daily is kind of weird. All right. In this class, we're always going to be using 365. However, if you get into a more formal investing class, if you're like a business major, you'll probably see something like this. For some reason, they make daily 360 days, and that's to account for holidays, which is, I don't know, really weird. But for us, daily n equals 365. So A of t equals 1500 times 1 plus 0.12 over 365, all raised to the 365 times 3. So just give me another minute here. 365 times 3 and 360. I'm doing my calculator work off camera here. You get $2,149.86. All right. So as you can see here, the more times you allow the money to compound, the more money you get, which is a good thing. That's what you would expect. Okay. Now, the one thing that we didn't discuss, and I'm going to write this one more time here. The one thing we didn't discuss is when I highlighted all this right here, I said this is going to play a major role. In the next section, we're going to learn that if you allow the money to compound continuously, meaning nonstop, every second of every day the money is growing, we call that continuously compounding growth. And that formula looks like this. And this is what the definition of E is. So E, which I'm sure you've at least heard of before, is defined as 1 plus 1 over n, all raised to the n power. And as n gets larger and larger and larger, so as n goes to infinity, E will start to approach 2.71828 and a bunch of numbers after that. But that'll be in the next section. So I will see you in the next video. Bye.